Hi everyone, I'm Adrian Lai, a representative from DHI Singapore. We first would like to thank the organizer in organizing these interesting competitions. And in this short presentation, I'm going to talk about our developed approach in detecting the leakage to tackle the problem posed by the organizer. This short presentation is organized as follows. We'll first go through quickly the background and objective of the competition, and then we will present our methodology as well as the results of our model, and finally the conclusion will be given. For those who are not familiar with the background of the competition, these slides will give you an introduction. So they are essentially sensors being deployed in an L-lown across the water distribution network. And the measurements were made for the whole year of 2018 with 33 pressure sensors shown in this figure. There are also 82 water demand sensors in detecting the water demand for each of the nodes. So in the competition, the repair time and location of the leak events happening in 2018 were recorded, and these are very useful for model development, which includes the process of calibration and validations. And the objective of the competition is to develop a model to predetect the time and location of the future leak events. And in particular, the measurements of year 2019 will be used to assess the accuracy of the model and will be used to justify which model is the best for the competitions. So now we are going to present our method or approach to detect the leakage of the L-lown. And this approach is an approach that essentially combining a water distribution network model as well as a deep learning model. For the water distribution network model, we have used EPANET for the purpose. And in this report in particular, we have used the Python implementation of EPANET for convenience, which is also named as Water Network Tool for Reliance, WNTR. And for the deep learning model, we have used a customized feed-forward deep neural network, which is built on the TensorFlow platform for building the deep learning model. And the first step in our approach is to have a good calibrated EPANET model because there are many possible parameters that can be tuned inside the model and they are unknown with the model that were originally given to us. So we need to do some tunings in particular of some of the parameters. And this figure pretty much summarizes what we have done, the steps that we have taken to calibrate our model. Basically, we have very different input parameters to the EPANET model, which include the pipe diameter, the pipe roughness, the residential seasonality, as well as the commercial seasonality. We vary all these parameters into the model using different combinations. And the results will give us a kind of error function in terms of pressure. And we have finally adopted the best model, which gives us the minimum mean square error of the pressure, and we adopt it as a calibrated model. And the detail of the calibrated parameters are detailed in the submitted abstract. And we are not going to give all the details here because of the limited time here. And next, after we have got the calibrated EPANET model, this model is used to generate random leak events for the deep learning model, for training the deep learning model. So the leak events have the following characteristics, and the leaks can have random leak location, random start times, and random leak duration as well. So we are using the EPANET model to create these artificial events for the learning of the deep learning model. And in our study, a total of 400 simulations with 50 to 500 leaking nodes have been adopted, and the outputs from the model are then fitted in the deep learning model. So basically, the outputs from the EPANET model are fitted into the deep learning model so that the deep learning model will can recognize what would be the signal pattern when there are leakage happening in the network. So going into more details of the deep learning model, it is a model that is developed based on the 33 sensors node using the simulated random leak events from the EPANET model. So this figure summarizes the model architecture of a deep learning model. So the input of the model are the pressure time series and the 33 sensors, which can be extracted from the EPANET output. And there are totally 5 hidden layers inside this deep learning model. And the output of this model would be the leak or no leak at each of the pipe, which is known from the EPANET model as well. And we have optimized the deep learning model based on different combinations of hyperparameters. And again, the details can be found in the submitted abstract. Going into the results, we have used the model to check with the 2018 data. Basically, it's an independent deep learning model testing using the 2018 pressure sensor data. And the comparison of the model predictions and the actual repair time, as well as the location, are given in this table. And we have selected the best model based on the correct location predicted, as well as the correct time predicted. And after selecting the best model, we have used the same model for the prediction of the 2019 leak location and time based on this optimized model. And the complete results have been submitted to the organizer. And this screenshot here just gives you a bit of the result that we have predicted using this calibrated or optimized model. So in conclusion, what we have done in here is that we have combined a water distribution model, water distribution network model, as well as a deep learning model to develop the required predictive tool. In the process, we have calibrated the EPANET model to generate random leak events, and these events are used to train the deep learning model. And the train the deep learning model is used to predict the time as well as locations of the leak at the L-time or of the L-town in year 2019. And thank you. This is the end of our presentation.